All right, this is going to be 11.5, part 2. There is one other thing I want to show you before we jump into lengths, and that's that you can use that formula from before to find the area between two polar equations. So instead of finding the area just from the polar equation down to the origin, you can find the area in between two functions in polar form. And all you have to do for that is this equation here, where you're going to do the 1/2 and then the r2 squared, which is the outside function, minus the r1 squared, the inside function. Of course, all this is really doing is just finding the area of the outside function and then subtracting away the area of the inside function that you don't care about. So I just wanted to show you this formula because I think you do have a homework question about it. These can get a little bit difficult, just to show you the example here in the book. So here we have this yellow line is a cardioid, and then we have the circle. And you want to find the area in the circle that's outside the cardioid, but it's just subtracting, so it's not too bad. Oh, God, sorry. Oh, that was gross. I'll edit that out. Probably not, I'll forget. Okay, so now we're going to jump into the lengths. So here, length of a polar curve. I'm going to go back to Word to write some of this stuff out. All right, so if we are looking at the length of a curve and we're given some function r is equal to f of theta, let's say we want to find this between two angles, alpha is less than or equal to r theta is less than or equal to r beta. Okay, so to do this, we're actually going to use the formula that we used before with parameterization. So we're going to use the formula for the length of a curve with parameterization. So I'm just going to remind you of that formula. So that was the formula between A and B. So this is where my parameter t goes from A to B, and it was going to be a square root. Okay, and then inside of the square root, remember that it was the derivative of the x function with respect to t squared plus the derivative of the y function with respect to t squared, all with the dt on the outside of the square root. All right, so this is just a reminder of the formula that we had for the arc length or the length of a curve using parameterization. All right, so now what we're going to do is if we are in polar form, we will parameterize polar equations using the following. And it's a very natural parameterization. We're just going to use those same equations that we looked at before and going back and forth between polar form and rectangular form. Those two equations are going to be r cosine of theta for x and then r sine of theta for y. Good. Cool. So these are going to be my parameterization functions. We just got to be a little bit careful here. So x is r cosine theta, y is r sine theta, and we're going to be plugging this x and y into my integral function here for the length. So what we end up with is that the length is going to be the integral. We want to think of our parameterization, our parameter variable being the angle theta. So now my A and B really are going to be my angles. So from angle alpha to angle beta still has a big square root in here. But then we're going to plug in the derivative of x with respect to the parameter. So this is going to be the derivative of x with respect to the angle theta. Sorry, I had to edit here a little bit because I goofed it up some. All right, so we have x is equal to r cosine theta, y equals r sine theta, dx dt. This is really going to be dx d theta that we're plugging in here. We have to take the derivative of this. But we have to be careful when we take the derivative of this because don't forget your r has thetas plugged into it. So really we're going to have to do some implicit differentiation here with respect to theta. It is going to be a product rule. So we're going to do the first, which is the r, times the derivative of the second, which is going to be negative sine theta. Plus the second, which is cosine theta, times the derivative of the r, which we'll write as dr d theta. And then I can't forget my cosine. Okay, so it's going to be that entire thing. That was just the dx dt. So dx dt, or really it's dx d theta for us. First derivative of the second plus the second derivative of the first kind of thing. All squared, and that's going to be plus the derivative of y with respect to the parameter. So we're going to have to do another product rule here. So first derivative of the second is going to be our cosine theta plus the second derivative of the first, which is going to give us a dr d theta, and then just copying the sign down. And that is all squared. And then we have a d theta outside. Okay, so all we did was we took our parameterization here for polar form, and we plugged that into the dx dt, which is really dx d theta and dy d theta with the d theta on the outside, and that also let us change our a to b to alpha and beta here. Now we just need to clean this up. I hope you don't mind if I just dot this, because it's pretty awful to begin with. So you would FOIL this stuff out, FOIL this stuff out. A lot of it would cancel out. In fact, I'll show you in the book how this works out. I just don't feel like writing it all out because it's not pertinent to you guys. Oh, they kind of skip it too. Well, I don't feel so bad skipping it if they just skip it. They just say it goes from here to here. So I'll do the same thing. In my notes, I have it all written out, but what's the point, right? So dot, and we end up with this. The arc length in polar form is going to be this equation. So it's going to be the integral from angle alpha to angle beta still has a square root. Inside of that square root, you're going to be doing the function r squared plus the derivative dr d theta squared, all with the d theta on the outside. All right, so this is the formula. When you go to take the test here in chapter 11, of course, the final exam, make sure you have this formula somewhere nearby in front of you so you can refer back to it. Let me get to the next page here, and we're going to do a quick example, and then we will end the video. So the example that we're going to do is we're going to find the length of the cardioid. Here, r equals 1 minus cosine of theta. So this is very similar to the cardioid that we did before. It just doesn't have that 2 out in front, so it's not quite as big. So just to graph it out, get rid of some of the stuff I was playing with before, sorry. We're going to be doing, it was 1 minus cosine theta. Okay, so this little cardioid here. So it starts here at the origin, at angle 0, goes out to 2. This is at angle pi, and then it comes back to 0 at the angle 2 pi. And then it just repeats that pattern over and over. We want to find the arc length, or the length of this cardioid, starting from the origin, tracing it all out, and then ending back at the origin here. Okay, so to do that, we're just plugging stuff into the function. To plug stuff into the equation, to the function, we are going to need to know the derivative of r with respect to theta. So let's go ahead and find that before we get too far into this. All right, so that's just going to be taking the derivative of this with respect to theta, which is just sine theta. Not hard, right? All right, and then plugging it in. So now we're going to have my length, the total length is going to be the integral. You do need to be careful about your angles. We are going from 0, tracing the entire thing all the way to 2 pi. Then that's going to be the square root of, it's going to be your r value squared. So that 1 minus cosine theta, quantity squared, plus the derivative, which was sine of theta, squared, d theta. Okay. And now we just need to clean this up and simplify it down. So now my length is going to be the integral from 0 to 2 pi, still with the square root. We will FOIL out that first parentheses there. 1 times 1, it's going to be minus 2 cosine theta. And then negative cosine times negative cosine is cosine squared theta. And then sine squared, we'll just write like this, sine squared. Oops. Okay, great. So now this is something that shows up a lot for us. We have cosine squared plus sine squared. Remember, cosine squared plus sine squared is just a positive 1. And I'm going to add that positive 1 onto the positive 1 in the front. And we get this. So we still have the integral going from 0 to 2 pi. Still have a square root. But now we're going to have 1 plus 1 is 2, and the only other term that we have there is that negative 2 cosine theta, still d theta on the outside. If I can spell theta. All right, now we just need to do this integral, and it's kind of a weird identity that we're going to use for this example. This is something that we saw back in chapter 8 when we were doing the trig identities from before, so we're going to use the fact that 1 minus cosine of theta is equal to 2 sine squared of theta over 2. Okay, so this is just the double angle identity for cosine, I think. So just go up into that identity sheet that you saw for you, that I gave you guys from before. I'll just go ahead and write it out, I guess. So the identity would be this: cosine of 2 theta would be equal to 1 minus 2 sine squared. Okay. All right, so this is the identity that we're using. Maybe a different name for the angle is better here. Maybe if I just call it A in this side. So this is the identity. This is the identity that is on the sheet. Cosine 2A is 1 minus 2 sine squared A. So if we just add the sine squared over, subtract the 1, fiddle around a little bit with the negative signs, and then also using the fact that if it's cosine of 2A, I have that to get the inside the sine squared. Same thing here. Here I just have cosine of theta. I'm having that to be theta over 2. All right, just play around with it, and hopefully you can see where that identity is coming from. Plugging that identity back into my integral now, still the integral from 0, wrong button, to 2 pi. But now it's going to be the square root of this right-hand side here, 2 sine squared of theta over 2. And then we still have a d theta on the outside. All right. When we take the square root of both sides there, I'm going to just go ahead and factor out the square root of 2 to the front of the integral since it's a constant. And then the square root of sine squared, we're just going to go ahead and cancel out to just be a sine of theta over 2. Still with a d theta on the outside. All right, antiderivative of this isn't too bad. We still have the square root of 2 out in front. Let me get my special thing that I've been using. Okay, and then the antiderivative of sine of theta over 2. We're going to divide by 1/2, which is the same thing as multiplying by 2. And then the antiderivative of sine is negative cosine. And then this is going from 0 to 2 pi still. Oh, not 0 to 2, 0 to 2 pi. Okay, and so just to finish this up, plugging 2 pi into this. So we have this root 2 over 2 thing, or we'll just write it as 2 root 2. If I plug 2 pi in, it's going to be cosine of pi, which is negative 1. But we already have the negative out in front, so really it's positive 1, which means I get 2 root 2. Minus, if I plug 0 into this, I get cosine of 0, which is positive 1, but this negative sign makes it negative, so then I get a negative 2 root 2. Oh, sorry, the double negatives canceled out to be positive. I said that and I didn't write it. So we get this, and then adding these two things together, we get 4 root 2. Okay, great. So I know that this particular integral was kind of difficult just because of the substitution here, but hopefully the ones that you guys see on your homeworks aren't going to be this bad. And if they are this bad, I think you're just going to be using the same trick that I used here moving forward. But that's it for section 5, and in fact, I think that is it for the entire course, and this is the last video I'm going to be making for you guys.